we've got a function. Fairly complicated, and what we're going to try to do is use the second derivative test to identify the types of critical points. All right. First step, find the critical points. So we find the x derivative, and that's going to be 6xy minus 6x. Find the y derivative, 3x squared, y derivative plus 3y squared minus 6y. And we're going to set those equal to 0 because we're looking for critical points. Set those equal to 0. And the best, I think we can simplify this one most. Here we have 6x and y minus 1 equals 0. We can factor a 6x out of both terms there. This one, I guess we can divide by 3. Let's divide by 3. At least tidy up some of the constants. I think that's really the best we can do so far. So we have x squared plus y squared minus 2y equals 0. This example involves solving two equations simultaneously. And here we see something we didn't see in an earlier example. We have two possibilities right here, and we're going to pursue them both. So let's call it equation 1. Equation 1 says either x equals 0, that would make the entire thing 0 and would solve or set fx equal to 0, or y equals 1. And what we're going to do is put each possibility from 1 into 2. Let's say x is 0. Okay, then what does that tell us about the y value based on the second equation? Or what if y was 1? What would that tell us about x in the second equation? So let's see how that plays out. So x equals 0 in 2. Oh, I guess I should label it. 2, there we go. If x equals 0 in 2, then we've got 0 plus y squared minus 2y equals 0. Factor out a y. And so if x equals 0, we get y equals 0 and y equals 2. And that gives us two sets of points. So we've got 0, 0, and 0, 2 are critical points. So that was one branch. Okay, x could equal 0. If x equals 0, then we solve this equation using that. The other possibility was that y equals 1. If we put that into 2, then we would have x squared plus 1 minus 2. That's negative 1, so x squared equals, let's do it down here, x squared equals positive 1. And that gives us x equals positive 1, or could be negative 1 when we take the square roots. So we combine those. Y equals 1 could work with either x equals 1 or x equals negative 1. And that means, careful, x comes first. 1, 1, and negative 1, 1. Those are two x values with the same y value, are also critical points. So we've got a host of them here. We have 4 different critical points. Now, next step. Let's identify what kind of critical points they are using that new second derivative test. All right, we're definitely going to need more space for this. Oops. So our critical points are 0, 0, 0, 2, 1, 1, and negative 1, 1. We had our x derivative and we had our y derivative, and I just need to remind myself of those. 6xy minus 6x. And the y derivative was a little more complicated. 3x squared, 3y squared, 6y. 3x squared, 3y squared minus 6y. So what do we need next to classify the critical points? To classify each critical point, we need the x derivative twice, the y derivative twice, and the mixed partial derivative. We need those to compute our d value. So what I'm going to do here is try to build these up into a table just so we can maybe save some space. The x second derivative is 6y minus 6. The y second derivative is this with respect to y, that'll be 6y minus 6. That's right, okay, just a quick sanity check there. And last but not least, I'll take the y derivative of this and we'd get 6x. Then what we can do is look at our points. We can look at the point 0, 0 and say, well, what does this turn into? What does this turn into at that critical point? Well, at 0, 0, we have -6, -6, and 0. And so our d, which again is the product of the two direct concavities minus the mixed derivative squared, that's going to be 36. We'll classify it in a second. Let's just do all the values first. 0, 2, 1, 1, and -1, 1. 0, 2, that's our y value is 2. That'll be 12 minus 6. That's positive 6. Same thing here, positive 6. 6x, x is still 0. That's 0. Those two values multiplied, 36 minus 0 is 36. Going right along. 1, we'd have 6 minus 6, that's 0. 6 minus 6, that's 0. 6x would be 6. 0, 0 squared minus 6 squared minus 36 here. And 6y, that's 0 again. That's 0 again, same thing. And 6x, but x is -1. Have to be careful with this. Remember, this will be 0 squared minus 6 squared. That's positive 36 with a negative out front, negative 36. So let's do the two easy ones. Remember, easy way to remember d is it's the sign of the product of the concavities. Both concavities are different signs, it means you get a negative value. If you have two different concavities, that means you have a saddle point. 0, 0, and 0, 2 are a little more interesting. Here we have the same concavity, and if we scan across at 0, 0, the x and y concavities are concave, indicate concave down because the sign of the second derivative is negative, whereas these two signs mean concave up. Look at the shape, concave up, that's going to be a local min. Concave down in some other direction, that's going to be a local maximum. And that is how you apply the second derivative test. Let's just go back over the process briefly. We have a function. We first find the critical points, and that's a non-trivial task in most cases, but we can eventually identify points if we can solve these equations on the setting x derivatives and y derivatives equal to 0. We can solve for the critical points. Once we have the critical points, then we need to find all the second derivatives, both pure x, pure y, and mixed xy, get those as functions, and then we just go through the process of subbing each critical point into those, calculating this discriminant value, and using the rules we saw earlier for leveraging that discriminant value to identify the kind of critical point we're looking at. To wrap up this question, we would typically ask ourselves, are the critical points that we identified as local maxima and minima also going to be the global max and min? Well, let's take a step back and put their function back here, and we'll use that function and our insights about it to answer this question. If that's our function, and we know that there are critical points which are local maxima and minima, we have one of each, the question is, are they the global max and mins? And I would argue no. This function has no global max or min. And this goes back to our original analyses of functions, where we tried to imagine what these surfaces would look like, especially when x and y get very, very large. And just even seeing one cubic here I would say that as y goes to positive infinity, our function, whatever x is, this term is going to start dominating things. We fix x, this y cubed is going to be the most important term, and our function is going to go off to positive infinity, which means there's no single point which can be a global maximum. Likewise, as y goes to negative infinity, well, we're going to cube those larger and larger values. They're going to be large and negative. And so our function will approach negative infinity if x is kept constant on that. And all we need is one direction where our function grows unboundedly. And as soon as we have that, then there can't be a global maximum. As soon as we have a point or a path where the function drops off towards negative infinity, well, then there's no single lowest point, because I can always go lower by walking further out in the y towards negative infinity path. And so there can't be a global minimum. If I can always go lower, then there can't be a single point where there's a global minimum. And so this function does not have a global max and min. The critical points we found earlier are strictly local extrema. And the ones that we found were 0, 0, and 0, 2 are strictly local extrema. All right. So again, that's a fairly typical question involving second derivative tests and critical point analysis. We'll continue on with further examples as we go through the unit.